With this video, we are starting a new series on quantum computing. This series will have 3 modules: quantum computing 1, quantum computing 2, and quantum computing 3. This is the first video for quantum computing 1, where the basics of quantum computing will be described. Now, let's first talk about what all this noise about quantum computers is. Every day we are hearing new news about quantum computers and what they can do. But let's first clear a few things about it. Any function computable on a classical computer is computable on a quantum computer as well. The converse is also true. That means any function that is computable on a quantum computer can be computed on the classical computer. Now, the question is about how much speed up you can get from the quantum computers. So far, quantum computers have not solved any NP-complete problem in polynomial time. So this also is one point that we should clarify upfront. However, there are a large class of problems of interest in everyday life for which quantum computers have indeed provided exponential speed up. One of the first such algorithms was Shor's algorithm. This is about getting prime factors of large numbers. It is known that classically there is no efficient algorithm available which can provide the prime factors in an efficient way. And in fact, this is the basis of RSA and other cryptographic algorithms that we are using nowadays in everyday life. However, Shor's algorithm that came up in early 90s showed that if you have powerful quantum computers, then this problem of prime factorization of large numbers can actually be solved in polynomial time on the quantum computers. So that made a lot of excitement and a lot of worries because, as we said, that RSA is the basis of most of the cryptography algorithm available today. Now, after that, there is another very important algorithm that is solving systems of linear equations that we do on an everyday basis in regular computers as well. So in around 2010, an algorithm by 3 people with names HHL provided a quantum algorithm which also gives a quantum speed up for solving linear equations. And in fact, that algorithm can be used to get the matrix inverse and so on also. Another very important algorithm that we have been using all the time in classical computers is the Fourier transforms. Like FFT, we know. Once FFTs came in early 60s, it basically changed drastically the signal processing algorithms, and that was used in many, many other applications as well. So corresponding to that, there is a quantum Fourier transform today that also provides a quantum speedup compared to even FFTs. And in fact, that can be used to find the eigenvalues of many matrices, which has many applications as well. Because of these algorithms, which provide quantum exponential speed up over the classical algorithms, these are being used extensively today in quantum machine learning to speed up the machine learning algorithms as well. We know that machine learning and AI are being used everywhere in all applications today, and increasingly they will dominate the general scenario. But we also know that because of the huge dimensions of the data and the large number of training samples used in machine learning to train the machines, a very, very large, intensive computing resources are being used for those purposes. But if we use the above algorithms of quantum computers, then we can indeed solve those machine learning algorithm problems much faster. And therefore, there is an intense activity in quantum machine learning as well. We will study quantum machine learning in module 2 of this series. Not only we have exponential speed up of the above algorithm, there are other very important problems in real life that may not provide quantum algorithms for them may not provide exponential speed up, but certainly polynomial speed up. And one such major algorithm is Grover's algorithm. This provides quadratic speed up for search and as well can then provide quadratic speed up of many combinatorial optimization problems, which are very, very useful in real life. We will study all these above algorithms as well as Grover's algorithm in the first module of this quantum series. Now, so this should give you enough motivation to study quantum computing and follow up in this quantum series. But in addition, there are other applications which are equally exciting. In quantum communication, for example, above we mentioned that because of Shor's algorithm, RSA algorithm used in cryptography has been threatened. However, on the other side, for cryptography itself, quantum computing offers a very new type of uh, algorithm called quantum key distribution, which can be used to for two people to share a secret key among themselves on a public channel. So therefore, maybe RSA will no longer be used as quantum computers are going to be becoming more and more powerful, but another quantum algorithm has been provided to take care of the cryptography um, techniques via quantum waves. And in fact, because of Shor's algorithm, a new area in the classical cryptography called quantum post-quantum cryptography has recently been started, which can withstand the quantum computers. Another very important area that is influenced by quantum computing is modeling of fiber optic channels in communication. We know that most of the communication today either is carried by wireless channels, which is on in the last mile on the cellular phones, but rest of the communication takes place today on the fiber optic channel. So far, fiber optic channel as being modeled as classical channels and communication takes place on them as classical channels. However, we can model fiber optic channel as quantum channels as well. And if you do that, then it increases the channel capacity of such channels. And this is very, very important because most of the communication is taking place in fiber optic channels. So this is another important application of quantum computing, which leads to quantum communication as well. Now let's talk about what are the differences between classical computers and quantum computers, and these differences lead to the speed up that we have talked about for quantum computers. There are three main differences in quantum computers from the classical computers. One is the superposition of states. In quantum computers, unlike in the classical computers where bits take value between either 0 or 1, in quantum computers, there can be a superposition of states. And because of that, we can get unprecedented parallelism in quantum computers, the kind of parallelism which is not possible in classical computers. To get parallel computing in classical computers, you have to have parallel hardware channels. If you want n times the parallelism, then you need at least n hardware channels. However, in quantum computers, using a single hardware, you can in fact get a very large amount of parallelism. And this is indeed a very, very important reason why quantum computers are so powerful compared to the classical computers. Another very important resource in the quantum systems is entanglement. This historically has been also very important and was a source of controversy in quantum mechanics. However, it has turned out to be a very powerful resource for computation and communication in quantum computing. And as we go along in this series, we will explain what entanglement is and how it can be used in quantum computation and communication to increase their efficiencies. One another difference between classical computing and quantum computer is that in quantum computing, all computations are reversible. But in the classical computers, of course, reversibility is not guaranteed. Some uh, operations are reversible and some are not reversible. So this has certain applications which we will not directly discuss in this series. Okay, as we said, in this series, there will be three modules. One is quantum computing 1, quantum computing 2, and quantum computing 3. In quantum computing 1, which is starting with this video, we are going to discuss the introduction of what quantum computers are. We are going to talk about the quantum axioms, quantum mechanics, the axioms of quantum mechanics, which are different from the axioms of the classical mechanics. And these are the axioms which make it possible for quantum system to be what they are. Then we will discuss about quantum gates like classical AND gate, NAND gate, and so on. There are corresponding quantum gates. We'll talk about them, which build the quantum circuits, just like the classical gates make the classical digital circuits. So we'll be talking about the classical circuits then. And finally, we will talk about the quantum algorithm that we have mentioned earlier, Shor's algorithm, Grover's algorithm, Fourier transform, and so on in this module itself. In quantum computing 2, we will discuss the quantum machine learning algorithms and something called adiabatic computing, which is a different mode of computing in quantum system than what we are talking about in quantum computing 1 using gates. So that will also be discussed. And adiabatic computing has become increasingly popular because the adiabatic computers are available on a larger scale than the quantum gate computers. In quantum computing 3, we'll talk about quantum communication, quantum information theory, as we discussed, fiber optic channel can be modeled as a quantum channels. So those basics will be discussed here. QKD algorithm that we just mentioned, quantum algorithm which can be used in cryptography. We will discuss that as well. And we will also tell how the RSA is broken by um, the Shor's algorithm. We will also discuss in quantum computing the basics of quantum error correction codes, which are essential not only in quantum computers, but also in quantum communication. We'll briefly discuss about state detection in quantum systems, which are the basis of quantum radars, which are strategically and otherwise become very popular nowadays. At the end, we'll briefly discuss about the quantum function theory. All of these topics that we will be talking about in quantum computing 3, each one of them can take substantial amount of time. So what we will be doing here is giving the introduction of some of these topics and tell the basic concepts there. Okay, now let's start discussing the quantum computers versus and their comparison with the classical computers. In classical computers, the basic unit of information is a bit. Bit can take value 0 or 1. And then in the registers that we have in the classical computers, they are made up of multiple bits. In quantum computer, the basic unit is called qubit. Qubit comes from its short form of quantum bit. So in quantum computers corresponding to bit, there is this unit called qubit. But however, this is somewhat different as we explain now. In case of one qubit, also there are two states called a ground state denoted by a 0 in this notation and an excited state denoted by 1. A qubit can take any value which is a superposition of 0 and 1. So qubit state can be denoted by this phi, which is equal to A0 plus B1, where A and B are complex numbers such that mod of A square plus mod of B square is equal to 1. The interpretation of this qubit being in this state is that it is a superposition of state 0 and 1, and it is in state 0 with probability mod A square and is in state 1 with probability mod of B square. So this shows the difference between a qubit and a bit. A bit can take only one of these two values. Qubit can take any value here. This is an uncountable number of values that a single qubit can take. Classical qubits, if there are classical bits, if there are 2 bits, then they can take value 0, 0, 0, 1, 1, 0, 1, 1. 2 qubits can take values as a superposition of these states 0, 0, 0, 1, 1, 0, 1, 1. So superposition of that is A1 0, 0 plus A2 0, 1 plus A3 1, 0 plus A4 1, 1, where A1, A2, A3, A4 are complex numbers and they satisfy mod of A square summation is equal to 1. So this represents a state of 2 qubits. If you want to represent this state, then you can store it as these numbers A1, A2, A3, A4. So once you know that, then we know uniquely what state it is in. Now, looking at this 2-bit system and 2-qubit system, the classical 2-bit system state requires 2 bits to store. It is in one of these states and you can store in 2 bits. The quantum 2-qubit system requires these 4 numbers to be stored, which are each one of them is a complex number. So in n-bit classical case, you need n storage units. For n qubit state, you need 2 raised to power n complex numbers. And remember, complex numbers here, and these are just this many 0 ones. Now, to store any one of these complex numbers can require a lot of number of bits. So therefore, to store even a 2-qubit state in a classical computer, it can indeed require a huge number of storage elements depending upon to what accuracy we want to represent these complex numbers A1, A2, A3, and A4. Now, let's talk about the classical and quantum gates. So we have just compared the bit and qubit. Now we compare the classical gates and the quantum gates. In classical gates, classical gates are AND or NOT or combination of these things. These gates transform bits. So you can take an input of 2 or more bits and output of AND will be 1 bit. So it transforms bits to bits. So you can think of these as well as their combinations forming digital circuits as mappings F from 0, 1 to the power n to 0, 1 to the power m, where n, m are non-negative integers. In quantum case, the gates map qubit states into other qubit states. So it corresponds to the classical case where the gates map bits into bits. here qubit gates, quantum gates map qubit states into other qubit states. And examples here are for one qubit, I, X, Y, Z gates. These are called poly gates. These compared to classical case where and, or, and not were the gates. So how these gates operate? This I is the identity. So this is the same as what I have written here. I operating on any qubit state will give the same qubit. So this is the identity operator. This X of gate here, X will take 0 state and convert to 1, and 1 state and it will convert to 0 states. Don't confuse these quantum 0-1 states with the 0-1 state in the classical case. So that's why these are represented differently. So in quantum case, X gate represents the NOT gate that you are here, because NOT here takes 1 to 0, 0 to 1. In this case, quantum gates takes 0 state to 1 state, 1 state to 0 state. All these operators or the quantum gates that we have are unitary operators, which means that these are reversible and these are linear operators. Now, in the classical case, the operators, the gates don't have to be linear. Now let's discuss about the prerequisites before we start getting into the details of quantum systems and quantum gates. We have so far just given an introduction and showed the basic differences between quantum bits and classical bits and the gates. We will be using basically vector spaces, linear algebra. Linear algebra is an essential requirement to study quantum computing. So in this case, we talk about vector spaces, and we'll be talking about vector spaces in finite dimensions. And the field corresponding to this will be the complex field. Often you can talk about vector spaces in some other fields. For example, it could be real field, but here the field that we choose is the complex field. Now, so we are assuming you know what vector spaces are, and we start from there. A linear map A from vector space V to vector space W is a map which is linear and takes elements from here and map to this. You can represent A as a matrix if V has dimension n and W vector space has dimension m, then this linear mapping from V to W can be represented by a matrix of dimension n cross m. Of course, this matrix, the specific matrix that you come up with corresponding to a linear map will depend on the basis that you choose in V and W. But let's just not discuss that and consider linear map A to be a matrix of dimension n cross m. A is a normal operator, linear operator, if A is star is equal to A star A, where A star is adjoint of operator A. So you take operator A, you can represent it in matrix form, then the matrix form of A star will be take the transpose of this matrix and also take the complex conjugate of all the elements in A. Then the corresponding matrix will represent A star. So A is normal operator if A is star is equal to A star A. A is a Hermitian operator if A is equal to A star. That means in this case, A is symmetric and actually symmetric, and you have to take the conjugate, then it will become A star. A is a unitary operator if A is star is equal to A star A is equal to I. That means A has inverse of A is A star. Unitary and Hermitian matrices, these two that we have explained, are normal matrices. If matrix A is of size n cross n and x and lambda are, x is a vector and lambda is a complex number, x non-zero vector such that Ax is equal to lambda x, then lambda is called the eigenvalue of A, and the corresponding eigenvectors is x. Now let's discuss very briefly the properties of the linear operators that we have studied here. A is a normal operator. Okay, we define it. If A is normal operator, then it is unitarily diagonalizable. So we can diagonalize it, and in such a way that the matrices associated with that will be unitary matrices. If A is Hermitian, then its eigenvalues are real. In general, for a matrix, n cross n matrix, the eigenvalues can be complex. But if A is Hermitian, then its eigenvalues are real. If A is unitary, then its eigenvalues have absolute value equal to 1. But in this case, the eigenvalues can be complex. For the finite-dimensional vector space V, you can always define an inner product. And as mentioned earlier, we are going to have vector space with field complex number. So on this vector space V, we can define inner product, which is denoted by this. This is a mapping from V star V to C. And this mapping has the following properties. If you take any x in V, then inner product of x with x is greater than or equal to 0. And it will be equal to 0 if and only if x is 0. Inner product of x and y is complex conjugate of the inner product of y and x. And this operation is linear in the first argument. So because of this property, then it will be antilinear in the second component. This is the standard way in linear algebra that is explained. But in quantum mechanics, this point is reversed, that the inner product is linear in the second argument and antilinear in the first argument. So which is what we will be taking going forward. Norm of any point x in V, which is denoted by the symbol, will be given by square root of inner product of x. X norm can be given in other ways also, but this is how we are going to take. Trace of the matrix A, which is denoted by trace A, is equal to the sum of the diagonal elements of A. If inner product of x and y is equal to 0, then x and y are called orthogonal. Now we talk about the tensor product of vector spaces. Tensor products are very much needed in quantum mechanics and quantum computing. Tensor products are usually not taught in linear algebra courses, but it is essential for us to go forward. So we'll be briefly talking about what the tensor product is. If V is the vector space and X is belonging to V is a vector, now so far we are writing X vectors in V like this. But in quantum mechanics, they use Dirac notation, where this vector X will be denoted by this symbol. And if you remember, in the beginning of this lecture, we started with states 0 and 1. They were given in this notation. So any vector X in quantum mechanics using Dirac notation will be actually denoted by this. X star is the adjoint of X, and that in that case, that is denoted by taking just this triangle symbol here, X, and then this. Tensor product of two vectors in V, or they can be actually, X can be in vector space V and Y can be in vector space W. So the tensor product of them is given by this vector, where so X, elements of X are denoted by X1 to Xn, elements of Y are denoted by Y1 to Ym. Then this tensor product can be given by this column vector, where the elements are x1, y1, x1, y2, x1, ym. It goes on like this. Then x2, y1, x2, y2, and so on, all the way till xm, yn, xn, ym. Therefore, the dimension of this tensor product vector is n into m, while these are dimension n and m. If V is a vector space, W is another vector space with dimension n and m, then the tensor product of the vector spaces denoted by V tensor, this is the tensor W, is this vector space of elements of tensor products of the elements of these two. So X is a element in V, Y is an element in W, taking X in a tensor product Y will be an element here for any X here and any Y here. So this way we obtain a vector space. If I is equal to 1 to n, are the orthonormal bases in V, Fj, j is equal to 1 to m, are the orthonormal bases in W, then the orthonormal basis of V tensor W is EI tensor product with Fj for all I and j. So the dimension here is going to be n into m, because the vectors, which are the tensor product of the elements here, and they have the dimension of n into m. So the dimension of this vector space, tensor product vector space, is n into m. And if this is going to have an inner product, and this has one inner product, then this vector space that we are obtained also has an inner product, which is given by, if phi is a vector in V, psi is a vector in W, then phi, and similarly, phi prime is vector in V, psi prime is a vector in W, then phi tensor with phi prime is a vector in this, psi tensor with psi prime is also a vector in this, and the inner product of them is defined by this. You take the inner product of the first components here and multiply with the inner product of the second components here. So this is how the inner product in this space is given, and this is also an inner product space. Linear maps. If A is a linear map from V1 to W1, B is a linear map from V2 to W2, then we can define a tensor product of maps A and B to be linear maps from tensor product of V1 and V2 to tensor product of W and W2, and it is defined as follows. A tensor B operates on the element phi tensor psi. Phi is element of V1, psi is element of V2. This is element of this tensor product, and the mapping is given by A works on the phi, B works on the psi, and you take the tensor product. This takes values in W1, this takes value in W2, therefore this tensor product takes values in this space. Okay, with this we end today's video. We have explained to you why we should be studying quantum computers. They are becoming increasingly important because as time is passing by very rapidly, we are getting quantum computers which can be used in real life. And we have explained the differences between quantum computers and the classical computers and the benefits quantum computers give. And we have also given the prerequisites in terms of linear algebra in this video. In the next video, we will start with the quantum axioms, the axioms used in quantum mechanics, which will be central to our continuing further. Thank you very much.